So once again, we are back and we are going to discuss today about the moment area method, right? So this method has two basic theorems, right? The first theory is, right? So integration of theta right is equal to integration of m over ei. This is for a particular beam, right? Let me draw again. Let's say it's from A to B. Okay, the second theorem defines the second theorem states you don't worry, we will discuss each and every theory very simply in fundamental way. So in delta EA yes it is E over EI. So now the change is multiplied by x bar, right? So this is really the first moment of area, right? So how can we relate this? So most first theory tells you that if you get a beam, right? Let's say if you have some load and it will deflect like this, right? So it says the difference between two slopes at particular joints. Let's say here, I take this point, I take this point, I show this A, I call this B. Okay, so I need the slope, right? The slope. Okay, so what happens is here there will be theta A, and here there will be theta B. So what really means is the difference between thetas from A to B. So that is, so always consider if it is B to A, so that means B with respect to A. So that means theta B minus theta A. Okay. So for now we will replace this. Okay. Theta B minus theta A is equal to the area of M over EI diagram between A to B. It's very simple, right? So if you draw bending moment for this, so the beam is sagging, right? You will ended up with a B bending moment like this, right? So let's hope A is here and B is here, right? So once you take bending moment, it's just a matter of time you divide by EI and it is M over EI, right? It's very simple. But remember, if you have some varying cross section like this, okay, so this is 2EI and this is EI. So you will have to divide these length, sorry, the values by 2EI, and here you will need to divide it. So it will remain same, right? It is for EI. So in here you will have to make these heights by half of it. So it's very simple. Whatever after you draw in the bending moment diagram, you just need to divide it by the EI value, right? So it tells you the theta between these 2 points, right, is equal to the area under moment M over EI diagram between those 2 points. So it's very simple theory, right? And the second theory, right? So the second theory says you, right? So let's call this A. Let's call this A and let's call this corner B. Okay, it's corners. So it tells you delta B over A, right? So this really means the vertical tangent, okay, okay, so here we can draw this tangent like this, right? So I need to remove, yes, this is too much. Write that again. So let me draw it like this. So we'll hold it this way. So we can assume any type of loading, right? It doesn't really matter. This is for the derivation. So let's consider the tangent A is like this. And tangent B is like this. Okay. Okay, all right. So this is delta A with respect to B, right? This is delta B with respect to A. So that means vertical intercept between B and A with respect to A, right? So this is vertical intercept between tangent A and tangent B with respect to tangent B, right? Sorry about that. So here always the P refers to, right? So you are taking that particular point and with respect to A, tangent at A, right? So what that theory mentions you is this is equal to the first moment of area, right? So let me draw the bending moment diagram. Let's say it's like this, right? So just arbitrary curve, right? So it might not be the actual shape. So We'll hope something like this, more realistic. So let's hope this is your bending moment diagram. Okay. So what happens is, so the point tells you, the first point tells you where you need to take the moment of area. Always here you should take the moment of area from A. Here you should take the moment of area from B, right? So it's between A and B, so you need the total area, right? So the total area is same for both, right? Even if you take delta BA or delta AB, the total area is same, right? M over EI diagram. So this is M over EI, right? So we will later consider the sign convention, right? So this is just same, right? But what is different? So you need to know the centroid to from this area, from this point, right? From this point, if it is, let's say this is, it's like here x1, let's call it x1 bar. From B it's x1 bar, and from A it's called x2 bar, right? So what can you say? So this is the most important concept, right? So don't get this wrong, right? So delta BA, so that means the vertical intercept between tangents from tangent at B with respect to tangent at A, right, is not equal to vertical intercept between tangents A with respect to tangent B. So this gives you the vertical uh, the intercept, right, vertical distance between two tangents drawn at 2 points on the elastic curve, right? It is not the deflection as well, it is, right? So this delta is not the deflection, right? Delta is not the deflection, right? So these two theorems are very interesting, but you can find the deflection on one condition, right? Because these two are just the vertical distance between two tangents drawn at 2 points on the elastic curve, right? So you can see probably even if it is same area, the x bar is different, right? So the first letter tells you where to take the bending moment. The most first theorem is, so this is the second theorem, right? So the first theorem says theta between these 2 points, right? So theta B minus theta A. So that's called theta BA, theta B with respect to theta A, right? If it is theta AB, then it is theta A minus theta B, right? So that's area under. So this area will give you, so it's only this area, right? So these two are the theorems. So it's very easy once you do a couple of examples. Let me go back to some example, right? So we will deal with this kind of problem. So let's consider here a beam with fixed support and a point load. So at the last lecture, I discussed about the degrees of freedom. So you have vertical load only, right? You don't have any horizontal loading or so whatsoever. So even if you are working on 2D problems, you will have 3 degrees of freedoms at a joint. So if a fixed joint, it restrained each 3 degrees of freedom. So that means you have 3 reactions to solve. But since you don't have any horizontal loading, you know that horizontal reaction is 0. So you will be ended up with vertical reaction and the bending moment. So you can just take it. So I will take the horizontal thing, and it's gonna be on the upward. So v minus p is equal to 0, right? V is equals to p. So sigma m around this, so I'll call this a, and here b. Okay, use the different color, right? So here a and here b. Okay, so sigma m you can take, it is m clockwise plus v is not coming, then p into this length is L. So I'm ended up with m is minus PL, right? Is that right? Yes, right? And if you really want to draw the bending moment curve, so you need, now you can cut it from here, and you remember, you cut it, take another clockwise bending moment. So here it's minus PL. Sorry, if it is anti-clockwise, its direction is correct, okay? It's anti-clockwise, positive PL. If it is clockwise, negative PL, right? So here it's P. Here you have left up, right, down, right? So this is the shear. So I can take bending moment M plus M minus PL. So this is X plus Px is equals to 0, right? So my M would be P L minus X, right? So at x equals 0, you have the highest bending moment, right? It's PL. So it's somewhere around here, and x equal to L, it's 0, right? So your bending moment will be like this, a triangle, right? So since the EI is same, I can divide it by the EI and say it's just M over EI diagram, right? This is actually M is PL. Here at this point, right? So now just draw the beam, right? Just draw the beam. So the deflection of that beam is like this. So this is the original position. So the final will be like this if you load it, right? So this is A and this is B, right? So at A, what is theta? It's a fixed support, right? It does not allow any rotation. So that is theta A is 0. So the tangent here is horizontal, right? Tangent A, right? So the tangent at B, you can draw like this. It's tangent at B, right? So this is, I will call theta B. So theta B, right? So the first theorem tells you, so you need to find theta, so slope and deflection at B, right? So this, so you need to find slope, that means theta, and deflection at B. So you know, from the first theorem, you can write theta B A. So theta A, right? So that's the area under this curve, right? Between A and B. So it's a triangle, and PL over EI into the length is L. So it becomes PL squared over 2EI. So it's positive, right? Positive area. So that means theta is clockwise. If it is negative, so that means theta is anti-clockwise, right? So make sure that you get the concept, right? It's theta B minus theta A. You need 2 points, right? So what happens if you select something, some point like this? Just say you know the area between this point, but you don't know the theta, right? You don't know the tangent, right? This is very critical. So here we know theta A is 0. The tangent is horizontal. So it is just theta B, right? So once you are taking, so even from this example as well, let me draw. So it's like, if it is like this, so you need to find theta at here. So you need to consider another point, but can you take this point? No. A or B you can't take, because why? There's actually theta. There's actually theta B. So that means you need to find theta A, theta B as well. But if you take here the maximum deflection point, at the maximum deflection point, let's say D, we know for sure at the maximum deflection theta D is 0. So it's better to take theta CD. Then it becomes theta C minus theta D. And this is 0, right? So you need to consider then the area between D and C, that's theta. So this, if for a symmetric case, this D will lie exactly in the middle. But the load is, let's say you load it, let's do some example. First we will try that same example for the second theorem as well, right? So clear everything. So this was the case. If you draw it like this, so the beam would look like this, right? So this was your bending moment diagram, right? PL over EI, and this length is L, right? What the second theorem tells you. So it is delta B A, right? So the tangent at B, tangent at A, tangent A, tangent B in the elastic curve, right? So since the tangent A is horizontal, right? If you consider any point on the elastic curve between the tangent A and that point will give you the deflection. This is a special case, right? If you consider C and so if you consider C and B, so you can take delta CB, but it's not the deflection between, right, C and B. But here you can see the tangent, since the tangent is horizontal, so you take the vertical intercept from horizontal line to the elastic curve. So what is that? That is the deflection, right? So this is the deflected curve. In the theorem itself shows the vertical intercept between two tangents drawn from 2 points along the elastic line. So it is not deflection. Why? One of those are not horizontal, right? But what happens if one becomes a horizontal? So that means we know theta is 0, right? So then we know, then we can take, right, it is the deflection at B. So get the concept right, okay? So the theorem say it's not the deflection, but you can find the deflection given that, right, your one of the tangent is horizontal, right? One tangent is horizontal, then from the horizontal to the elastic curve gives you the deflection, right? So it's pretty straightforward. So you can just take here, so delta BA. So the moment between, so we took the area in the previous case, PL squared over 2EI, okay? This was the area, and be careful then how to take the moment of this area. So you should consider it from the first letter. You should take moment from B. So distance to centroid is how much? 2L over 3, right? So this is 2L over 3. So it's becoming PL cube over 6EI, right? Is that right? No, it's getting cancelled, right? So this is 3EI. So this is the deflection. Why? The tangent A is horizontal. So if you want to find deflection, make 2 points, but make sure one of them are tangent. at where the tangent is horizontal, actually, right? So if you found two tangents where the both tangents are not horizontal, your life would not be very easy, right? So one more thing is we do an example like this. So this is the Morse second theorem, right? So let's consider an example like this. Draw it. So beam supported, have 120 kilonewtons. So this is 10 and this is 5. This is 120. Okay. Okay. So yes, you can calculate the bending moment diagram. It will be, so I'm not wasting the time to draw it, right? So it would look like this. Right? So your maximum bending moment will be around 400, right? 400. So I'll just divide it by the EI, so then I get the M over EI diagram, right? Okay. And please consider now the load is not acting at the middle, right? So if you draw the deflected curve, right? It would look like this, right? Right. So the point is the maximum deflection does not occur under the load, but the maximum bending moment occurs underneath the load, right? This is the maximum bending moment. It happens underneath the load, but here is the maximum deflection, right? So get the things right? So that is the point where you have a horizontal tangent, right? Where theta is 0, right? So this distance you don't know. Please don't be confused. The maximum deflection is not underneath the load, right? It's the maximum bending moment. If you just take a flexible ruler and apply some load like this, you will see the maximum deflection would be somewhere around here. But the maximum, if you draw the bending moment diagram, the maximum bending moment is just underneath that, right? So the maximum deflection is somewhere here. So I will consider that as xm. Okay. So for that, I will take, this is the bending moment, right? So this is xm. Okay, so from the similar triangles, I can take 400 over EI over this length over this length, that is 10, is equal to this this height over this length is this height over this length. So that is the height we need to find. So that is M. I'll call this M. Okay, now I'll call this Y. Okay, Y over how much? It's XM. So I got Y as 14 over EI. Get the concept again. So if your point load is exactly at the middle, so then you know your bending moment is bending moment diagram is symmetric exactly at the middle when you, and the maximum bending moment is PL over 4, and it happens underneath the load, as well as the maximum deflection also underneath the load. But if you move the load, the system is not symmetric, right? You can't tell where the deflection would be. We need to find it, right? So it's just a matter of we taking it as XM, right? It's a common term. So still the maximum bending moment occurs underneath the load, but deflection is not, right? It's somewhere else. Maybe it's closer to this load, right? Maybe several millimeters away. We can't tell. We don't know, right? So what we know is, so we can go ahead. So what we need to find is the deflection, right? So for this deflection, so what will be the approach that I have to take? Just think about a minute. Right? So the easiest thing is, so you need to calculate either value of this, right? Delta D. So with respect to A, right? So this is Morse second theorem, right? So if you take this, that's quite okay, because the tangent here is horizontal and the tangent here is like this, right? So from the elastic curve, you can take D, right? That's quite okay, right? So to find this, you need to find, okay, you need to find the area of bending moment diagram between D and, so let's call this D, let's call this D, okay, D and A, right? So you need to find this area. To find this area, you need to know how, what? So here XM is there, right? So you need to find XM, right? You need to find XM, right? So how to find XM? So you can find XM. So one thing is, so since your B is here, right? So you know delta BA. Delta BA is the end, first moment of inertia taken at B, right? Of this moment diagram, right? So it gives you this height, right? Not the deflection, it gives you this height. But what can you say about that height? That this is a triangle, right? So the thing I'm drawing in yellow color, and you know this is theta A, right? So delta A you can write theta A into the length, right? Since this is small angles, L into tan theta, right? So tan theta is equal to theta A, since small angles, right? So this is 5, the length is 5, length is 10, so it's into 15. So the theta A is delta EA over 15, right? Is the delta A over 15, right? So, and from here, so from here, right? So I need to get rid of this delta, right? So how do I get rid of this delta? So one possible thing is I can use Morse theorem, right? So delta BA I can find delta BA I can find how? It's so finally I need to come to here, right? So delta BA is the moment of area of this M over EI diagonal. So these are two triangles I can take each one. So from where I need to take the bending moment? Sorry, the moment from B, right? So it's half. This moment area is negative, right? So this is sagging. So you need to multiply this everything by -1, right? So it's 400 over EI, right? For this triangle, right? For this triangle into 10, right? Into 10 over 2. The distance is, this is 5. 5 plus 1/3 of this, right? From here. Because here it's 2/3 of 10. Here 1/3 of 10. So it's 10 over 3 plus 5. And the other triangle, half into 5, the length, over EI, right? So this is the Y value, and this is the length, this is half, and it's how much? It's 2/3 of 5, right? So if you solve it, you would get this as how much? Yes, minus 20,000 over EI. Is that right? Okay. So we found this, and this is equal to how? This is equal to theta A into 15, right? So theta A is, so we write theta A is minus over 15 EI, right? We found that. Now it's okay, right? So, so everything we are doing for a reason, right? And if you find theta A, right? So you can just find, so so how to find now theta, how to find x. So to find x, if you know theta A, theta D is 0. So that gives you can use what? The Morse first theorem, right? So theta D into A is equal to the area between A and D, right? So that's very simple. So theta dA means theta D minus theta A. This is 0. Why? It is the maximum deflection point, right? So theta is 0. The tangent is horizontal. So the area, right? So half. So this is also negative, okay? Area is negative. So half minus, so this triangle, right? Between D and A. So that height is 40 xm over EI into xm. So the negative value cancelled, and theta A, 20,000 or 15 EI, right? So from here you can take x as, so there's a x squared term, so xm will be 8.16, right, meters. So that means it is not underneath this load, right? So it's somewhere here. The length is 8.16. Can you see? It is where the maximum deflection occurs. But the maximum bending moment is just underneath the load, right? So after you find xm, right? So you can just find the deflection. So that's again Morse second theorem, right? It's the tangent, the vertical intercept between two tangents where one tangent is horizontal, right? The pretty simple, right? So we found the tangent, uh, the distance between tangent A is a deflection. So we found xm. So we just need to take the area of the first moment of area of this part, right? So it's pretty straightforward. So I will write. So yes, here delta dA, okay, the deflection, right? This is the maximum deflection, right? How? Because our tangent at D is horizontal. So the tangent drawn at A and the tangent drawn at D, horizontal and having some slope respectively. So the vertical intercept between A is at the horizontal level, the tangent drawn at. So the vertical intercept gives you the deflection, right? Because the tangent is horizontal, right? That's how, in this special case, you will end up with the deflection. If not, this cannot be always deflection, right? So you can take the area of that moment. So it's half into 40 xm I into xm is the area, right? So it's the area, and then what you have to do, you have to, so from here you have how much? One third of, right? So, so the final question, is this notation okay, right? Just clearly see, if, so we just only need this x bar value, right? If you find it, so because xm is already found, 8.16 meters, right? So just need to plug the, so here shall you see this, so it's d, right? So the tangent at here, right? So let's draw the tangent at a as well, right? So we need this, t, right? So you know, the distance between these 2 points is delta, how much? A d, right? Distance in the vertical intercept between A and D with respect to D, right? Here, how much? It's the stationary point. So we move the tangent here. So that means we take the tangent with respect to the extended tangent, right? It's delta d A. So here we extended the tangent at D. So it's with respect to D. Here we extended tangent at A, it's with respect to A. So what is actually D? This is not right. So the actual thing is delta A D, right? So I hope you clearly got this idea, right? Otherwise you will, otherwise you will take, okay, what to take, delta dA or delta AD. So from this method you can see what to take, right? So if you are taking at a particular point, you extend the other tangent to that point, and it's with respect to that tangent, right? So that means you take the moments about the first letter, that you have to remember. You take the moments about this. So if you need actually the delta dA, you need to take moments about moments about D, right? If you need moments about, if you need the, it's delta AD, you should take moments about A, right? So this x would be how much? 10 into, sorry, not 10, right? So this x is, it's 8.86 the total height. So what, two-third of that, two-third of xm. So once you simplify this, you will end up with this equal to 4245 over EI, right? So you will see this is not very straightforward thing, right? So you need to have where you get a zero tangent, vertical, horizontal tangent, and zero thetas, right? So you need to be tricky. if you have how to say varying loads, right, distributed loads, so your bending moment curves will look like curves, right, will be curves. So they are the taking moment of inertia, sorry, first moment of area, and the finding area is not so straightforward, but there are simplified assumptions that you can manage. But here's how it's done, right? So just consider if your load is somewhere else from the middle, so your bending moment is just about that, the maximum bending moment just about that loading point, but the maximum deflection point is not, right? Okay, thank you very much.